moving event data. So as I said before, you can now choose when you send an event between two capsules if you want the event data to be copied, which is the way it has always been before, or moved, which is a new possibility. And in this sample here, you can see how you can do it. So it is determined whether you are passing an L value or R value reference to this event constructor. So in the first case here, the usual way to do it, that will cause event to be copied or data to be copied. But if you pass an R value reference, then it will be instead moved. And one way that is quite common to get an R value reference is to use std::move. And of course, this requires that the event data type is movable, and that can be accomplished in two ways. If you have the data type defined in the model, for example, as a class, the most natural way is to create a move constructor for it. But you can also have a situation where the type is external, for example, an STL type like std::string, and then you can define a move function in the type descriptor, similar to how you previously did it, for example, for copy. And the move function in the type descriptor is a new function. It describes how to move data from a source to a target object. And like I said, if there is a move construct, the typical implementation would be to invoke it. But it can also be, for example, that you're working with types for which you cannot add a constructor, and then you can implement that in any way in that move function body. If you use this for a type alias, you should know that this is, contrary to other type descriptor functions, optional. So you'd only need to implement it if you need the type to be movable. And if you haven't defined it and you still attempt to move an object, then it will fall back to doing copy, just like before. So this is for when you're sending the event. Then you also sometimes want to move the event data when you're receiving the event in, for example, in a transition function. And for example, you may want to move it into a capsule attribute so you can use it later. And in the same way, then you can use the std::move for the RT data to avoid the copying, but that requires that RT data is modifiable, so it cannot be declared as const. So to accomplish this, we have introduced a new property on transitions called const RT data parameter, which you can uncheck if you want the RT data parameter to be non-const. And we did some experiments with sending a string 100 times between two capsules just to get a feeling for the performance improvement, and noticed that in that sample application we obtained about 35% faster performance if moving instead of copying the string. And in general, this feature is of interest if you have big data objects that you need to send, or if you have an object that you send many times, because then even if it's not so big, sending it many times can still accumulate to some delay, of course. So let's take a look at the tool, how this feature works. So here I created a very simple model, just having a top capsule that can send events to some inner capsule. And to start with, I will just use an empty class here, and I have defined one event E1 that takes this my class as an argument. And if we open the state machine of this top class or top capsule, we can see that I'm sending it twice. First time I'm sending it by copy, and the second time by move. And to see what happens, we can create a copy constructor and a move constructor on this class, and we expect it to be called once, first the copy constructor and then the move constructor. And yes, so we can see what happens. We can write output here. And in the same way, we will create a move constructor. And I will copy this text. And then let's build this application. And if I run it now, we will get first copied and then moved, just as we would expect. So now let's also try to avoid the copying when we are receiving the event. So here I have two transitions in the receiving capsules. First one triggered when we are sending the first by copy, and then on this T2, I'm receiving it. And here I don't want to be copied. So I can, and I have defined an instance of my class here, an attribute in my capsule, and I can assign that using the same way, but for update, like this. And now this is a call of the move assignment operator, so I can create it also in the class. Unfortunately, we don't yet have a special shortcut for doing it here. We plan to add that in the next sprint, but for now we can just create it manually, call it operator equal, and you can just copy this argument from the move constructor, and now we have created a move assignment operator. And print out there so we can see old that. So now we expect first copied moved and then the move assignment operator to be called. And you see that it's exactly what happens. So this was the simple example for a class that you have defined yourself with actually empty implementations of everything. Slightly more interesting example could be to use an external type. So here I have defined a type def of std : string. And you can see now that we have an additional move function in the type descriptor. So these implementations are quite simple. So for copy function, we just invoke the copy constructor, and for the move function, we just invoke the move constructor of the string. And the rest of the type descriptor functions are similar or simple too, like init, we just allocating, and we have defined also encode, decode, and destroy. And I have another event here typed by that, and a string argument for event 2. And now if I want to send this, I need to modify my state machine a little bit. So here I now need to define a string. Not be so big, but anyway, we will send it by copying first and then by moving. Like this. And in the same way we want to receive it, we need to change the trigger here so that we can trigger on E2 instead of E1. And same for this one. And then the code here also needs to be updated then, so that we assign it to a string variable, which is called S in my capsule. And otherwise it's the same as before. So let's save this now, and also I should mention that in these copy functions I have made a printout std copy, and in move I made a printout of std : move. So we expect these to be printed now. You can see the same thing happens. We got the call to the copy function and then the move function. And when we received here in the inner state machine, this is calling the move assignment operator of the string directly. So we don't have that represented in the model, and that's why we don't get any printout for this assignment here.